All right, morning. Let's begin a new unit on blood. So we'll simply just talk about blood, all the associated topics. One of my main goals today is to get you ready for Friday's lab, which is a blood typing lab. And so when I get to that part of the lecture, really focus that lab. If you don't understand it, it can be very frustrating. And when you work in groups, it's easy just to kind of hang back and get through the lab with absolutely zero understanding. So the way I try to make sure everyone's engaged is for that lab I give a little quiz where I have your group come up and I ask each person, each person in your group has to respond to a question. And it's a quiz. So that means you got to get it right. And it's face to face, so I'm a little lenient and patient because it's kind of nerve-wracking to stand there in front of you and talk. Although it shouldn't be, I do it in front of you guys, right? So I'm switching it a little bit. You just got to answer one question. That's all you have to do. And most people usually do okay. So to first understand blood typing, we at least have to know what blood is. Now, when the term whole blood is used, that refers to the fact that blood has all these subfractions. Blood is composed of subfractions, which can be seen when you centrifuge blood. Can be seen blood is centrifuged. You spin it down. Next slide shows that. Take a blood draw from the cubital vein there. And then it doesn't take long. I mean, I've done this. You just 5,000, 6,000 Gs of force for about 5 minutes. And then you can see the fractions of blood here, which include plasma, the straw-colored plasma. I'll just kind of go with the textbook numbers here. It's about a little more than half of blood, 5%. And this is the liquid part of blood, okay? Mostly water. Right between the top part and the bottom part is this slight layer called the buffy coat. And the buffy coat is less than 1% of blood. It's very important. It's a thin layer. It's white. And I should tell you what it's composed of. Part of it is white blood cells, and then platelets are also in this layer. Leukocytes and platelets. And spun down on the bottom, the red hematocrit are the erythrocytes. Which is about 45% of blood, sometimes called the hematocrit, which is print. Erythrocytes are the red blood cells. Urethra means red. Leuco means white. You haven't figured that out by now. Leuco means white. Urethro means red. Red blood cells white blood cells. Well, anyways, the plasma, bumpy coat, and erythrocytes, and the crit is basically what I call the subfractions of whole blood. Okay, that's what blood is. Here's a real picture of whole blood next to spun down blood. You can see the straw-colored plasma. And some other facts about what blood is. The pH of blood is slightly basic. pH of blood is slightly basic, but there's a range because venous blood has a slightly higher CO2 content, so that makes it a little more acidic. That'll be the pH of venous blood. And then that should be the normal pH of arterial blood. So within that normal range is the pH. And I've been saying all semester that the average blood volume is something like 5 liters. You know, a little bit more for men because on average men weigh a little more, so their tissues need a little more blood. So about 5 liters of whole blood. And some terms on the bottom there, I already defined what whole blood is. It's basically all the subfractions I just listed on the board, the plasma, the bumpy coat, and the crit down below. And the plasma is the watery part. Now serum, the one thing you may not know is if you siphon off the plasma and let it sit in a glass tube, the charged particles on the glass tube will trigger a clotting reaction. Okay, so you see a blood clot will form. And serum is basically plasma without the clotting factors. So if you don't need clotting factors for your analysis, you can just kind of like siphon out the serum. If you need the clotting factors, you can heparinize the tube, you can add things to prevent that coagulation, which we'll get to. You have to know how the blood coagulates. Okay? So that's one thing you'll learn. Blood will just clot by itself if you just let it sit there. And it won't happen for you as long as blood circulates and is flowing. You don't allow a chance for the clotting factors to accumulate. Okay? But we'll learn that when we get to it, how it needs to when there's an injury to the blood vessel. So some functions of blood. One is transport of the blood gases. The blood gases are transport of CO2, O2. Now I have a whole lecture on that in respiratory, so I won't really talk about it today. But I will say that oxygen is why blood is considered life-giving, because it transports the oxygen to the tissues in your body. That's the one thing you should take away from blood is that molecule, O2. Now, it does regulate pH, okay, I gave you the range, and body temperature because you have superficial or deep veins, and the arm is a good example for you guys because I taught some of those superficial veins, right? There's no arteries that run with them, it's all veins, so if you want to dissipate heat to the environment, you increase blood flow to the superficial system, and you can dissipate heat to the ambient air. Protection, when I give the immunity lecture, all I do is talk about white blood cells, so I'll kind of save it for that. white blood cells are in the blood too. So I wrote this on the board. It transports blood to tissue. So with this slide, I mean to teach students that, well, it's something you already know, right? Blood is oxygenated at the pulmonary capillaries. So you know your vasculature, it's on the x-axis here, and I put this little picture there when we talked about the capillary exchange, the blood gases, the oxygen diffuses to the tissues, and the CO2 is picked up by the blood. Okay. Well, this slide kind of shows you the breakdown of the subfractions, and what you see on the far left here is whole blood, about 5 liters. It's actually not very much of your body weight. It's about 8%. Okay. You have a lot of other fluids in your body, 92%, that is not blood, which is quite remarkable. That you only have these 5 liters that circulate it and keeps you alive for your whole life. And so, what we learned is that the blood plasma if you just look at the numbers, you just basically see that plasma is mostly water. It's like 92% water. H2O. Now, there's some other things in the blood, some proteins that are soluble in the plasma that are worth mentioning there. Albumin, these are all proteins that are soluble. Albumin is probably the most plentiful protein that provides that osmotic pressure of the blood. That's the pressure that retains fluids in the blood, so that's important. And there's globulins. Globulins are antibodies. Okay, we'll talk about those in the immune chapter. They circulate in the bloodstream. Fibrinogen, we'll try to get to that today. Fibrinogen is the soluble form. It's clotting. It's a clotting factor. In fact, it's clotting factor 1, which tells you it's the most important one. Also known as clotting factor 1. Roman numeral 1. Okay. There's other stuff in there. They don't list anything else, but that's good enough. There's also, besides proteins, all these things like electrolytes. Nutrients, gases, regulatory substance, waste product, line. Things I think you know, like sodium is an electrolyte. Nutrients like carbohydrate, fats, lipoproteins. Okay, the things that you may not know are the different kinds of white blood cells, or what they call formed elements. Right? This 45%. So you got plasma, and you have the formed elements. Now the formed elements, they were in the buffy coat and the crit, those subfractions. The erythrocytes. And they're called formed elements to be more direct. They're basically the blood cells, but you can't really call them that because a lot of them aren't true cells, but you can think of them that way. I'll show you how they're formed. But the formed elements include the white blood cells, sometimes I just go WBCs, the red blood cells, the RBCs, and platelets. And the white blood cells include all of these that are listed over here. The neutrophils, the lymphocytes, the monocytes, the eosinophils, and the basophils. The neutrophils, eosinophils, and the basophils. So these are names of white blood cells, and I'll tell you their functions later. I listed them as the first three because they're categorized as granular leukocytes. The cytoplasm has these dense granules that are filled with defensive molecules. I'll get into that later. And basically, the last two are agranular, the monocytes, lymphocytes. Again, the RBCs are what I called earlier the erythrocytes. They actually have the molecule hemoglobin. I abbreviate that HB sometimes. That carries the O2. So HbO2 is like oxyhemoglobin. Because it binds oxygen in the capillaries of the lungs. And the platelets are the thrombocytes. You have clotting factor 1, fibrinogen, but actually platelets can help, in some cases, initiate blood clotting. Platelets are also known as the thrombocytes. Initiate the blood clot. All right. There's a picture of the formed elements. The white blood cell, the red blood cell is red, and you see the platelets look like that. So that's a real photo. Okay. 3,500 magnification. I first want to deal with the red blood cells in this first part of the lecture here. And so let's kind of learn how the red blood cells are formed, hence the term formed elements. So you have to talk about the bone marrow for all the blood cells. Now I'm just going to show you just a nice little poster of the developmental pathway of from stem cell at the end, red blood cell. Erythrocytes, RBCs, the formation of them. So you have to think about the bone marrow. This all occurs in the bone marrow. In adults, bone marrow is only in a few locations inside bone. It's in the proximal femur, clavicles, flat bones like cranial bones, iliac bone of the hip. So that's where you got the red marrow, where all your blood cells are squeezing out of your bones every day, okay, in millions. And so the red blood cells, there's a stem cell in the bone marrow called the hemocytoblast. That cell, stem cell is a cell that has potential to become a different kind of cell depending on how it's stimulated. Okay, you set it on a different pathway. So a committed cell, a prourethroblast, is targeted by EPO, which is a hormone that'll send it along the pathway to become a red blood cell. EPO is a hormone from the kidney. The kidney regulates fluid levels. If fluid levels are low, you want more red blood cells. The crit will actually help the blood retain more fluids. So, and it also helps correct hypoxia. So EPO is important. Like I said at the bottom of the slide there, it's essential for differentiation past this prourethroblast stage. And break that word down. Pro, does it mean before or after? It usually means before, right? Because we're before the mature cell there. I usually take it to mean it means before. And urethral means red. Blast usually refers to a more immature cell. So when blast is a suffix used to describe a cell, it's a more immature form. There's probably something after it. So to get past that stage, EPO, you also need iron and B12. Okay, that helps too. Iron, vitamin B12. What you get from your diet. Okay, and that committed stem cell with EPO, you'll get to the developmental pathway, which has different phases. In that phase 1, they call it ribosome synthesis. So I'm going to try to train your brain. What's the most important thing I said about blood? What does it carry? Oxygen. The name of the molecule that binds oxygen, hemoglobin. So if you're a cell and that's your job, you have to make hemoglobin, the protein. So how do you make proteins? Well, you need the RNA, right? Like ribosomes. So in this stage, the cell, notice what color it is. I mean, it's not really purple. These are the color that when you dye the cells and they take up a stain and you look at them under the microscope, they present what's called a basophilia. These, what are they called? These urethroblast stage. Urethroblasts, they present a basophilia. That's that purple color you see there. Purple, blue, something like that. And when you look at that urethroblast, does it look larger or smaller than the cell here? It's a little bit larger, okay? That's correct. Does this cell have a nucleus or not? It does have a nucleus, ain't there? Yeah, wasn't that tricky? Now, as you go along here, you see how eventually you spit it out. Okay. Now, what's inside the nucleus? The DNA. So you need it now, right? Because it's like you have to make the hemoglobin. So you have to transcribe it, translate it into the gene for the hemoglobin. And so to make proteins, you need ribosome synthesis. It's like you're preparing to synthesize HB, hemoglobin. So think of it that way. And then you get to phase 2. You're making the hemoglobin, and they call it, well, you know, hemoglobin accumulation. And the name of the cell there is normoblasts. And they take up a different dye, eosin. Eosin is red, basophilia is purple. So the cytoplasm is less of a purplish, more of a reddish. Now what you don't know is when you stain these cells, you put both dyes in with the cells. And whatever the cell takes up tells you the stage of development, phase 1 or phase 2. So if the cell presents this eosinophilia, is what it's called. Eosin is the dye, eosinophilia. If it's like red or purple, you know what phase it's in, because now you're accumulating HB. When you've accumulated enough HB and you don't have to make any more, what you're doing is you're progressively spitting out all the cell organelles to get you're trying to shrink, okay? Cells shrink. And then eject organelles. You don't need them. All you need is hemoglobin, because that's your job. The last thing you eject is the nucleus, because once you eject the nucleus, you can't make any more hemoglobin, so you better be done. Once you eject the cell is called, well, that's called phase 3. The ejection of nucleus, and the cell is called reticulocyte. Okay? And it can enter the circulation. And then it takes its final form, erythrocyte. You usually don't see reticulocytes very often. If you do see a lot of reticulocytes in someone's blood, it probably means they're bleeding somewhere because they're losing a lot of blood, so they always have to replace it with these new cells of reticulocytes. But erythrocyte is what you should see. So it's basically a bag of hemoglobin. It's got no nucleus, so it's got no DNA. It's got no organelles. It just has the hemoglobin. That's all it can do. So this process from the prourethroblast to the mature red blood cell, I don't know if you can see that there. Tells you the time course. 20 hours, 3 days, gives you a rough idea. And in that time, you lose the RNA, the ribosomes, right, rRNA, and you kind of like increase the hemoglobin during that 1 to 3 day period. All right, so we have mature red blood cells now. Yeah, go ahead.
You know when they do, they check DNA for your blood, so
Yeah.
when you lose the nucleus, isn't that where the DNA is?
Yeah.
I'm kind of confused, so how do they check the DNA?
There's other other cells that have DNA, like the white blood cells.
Oh,
Yeah. Yeah, the red blood cells don't have a nucleus, so you're right, shouldn't do that. All right, so the erythrocytes. Here's some properties there. I have this on the slide. They're dedicated for transporting the respiratory gases O2, CO2, mentioned that. We have a biconcave shape. What does that word mean? Biconcave. Well, concave means like it curves in. So biconcave means it curves in from both sides. Okay. RBC characteristics. We just said a few, like they have no nuke, no organelles, and just bags of hemoglobin. This biconcave shape. So if you look at it from the side, instead of being like a regular round cell, it's like kind of like that, biconcave. Because it like curves in on both sides. So you have a high surface to volume ratio. Well, what that means is you have more surface area for gas exchange. Okay. That way, like if you have a lot of gas molecules in the center of a round cell, it's harder for them to get to the surface. So if you're flattened, it's easier for more gases to exchange. So you have 30% more surface area to exchange. And so, you know, all the cytoplasm is a short distance to the surface for easy exchange. You can see the importance of having this shape. So here's some numbers here. I would just kind of know this number, the diameter of the cell, 7.2 to 8.4 microns. Normal. Yay, right there. 7.2 to 8.4. And so I have a few images on the left. The top left in the blood smear, get our blood slides and just look at them. That's what they look like. You mostly see RBCs. They kind of like outnumber the WBCs like 1,000 to 1. And in fact, on this frame of view, I see no white blood cells. I do see little platelets. They look like dust fragments. Right there, those little fragments right there. I don't know if you can see in the back. Platelets are there. Okay. Mostly you see RBCs. Oh, that's beautiful. Cool. When you cut one open, now that's kind of the picture you get there. This phenomenon here, you know, it's good that these cells kind of shrink down a little bit as they lose their cell organelles because they have to squeeze through capillaries, and they do so single file. But because of their shape, they stack rather easily. Okay? And that phenomenon of their natural ability to stack is called rouleau. Stack of RBCs. Another characteristic is their hemoglobin. So what we learned about the structure of hemoglobin, it's a tetramer. Means it's got 4 subunits, 2 alpha, 2 beta chains. These are globin proteins, and in the center of each of these 4 subunits is the iron-containing heme unit. Okay, this is their iron-containing heme pigment, let's call it that. And actually, it's the iron that actually binds the O2. Okay, right in the center there, Fe Eris. That's what I say at the top there. One iron can bind one O2. Okay, so therefore, one hemoglobin has 4 hemes, so one hemoglobin can bind 4 O2 molecules. If an RBC has like 280 million hemoglobins, that means one RBC can bind over 1 billion O2 molecules. So to kind of make it a more usable number, you do the Avogadro's number thing, you do the mole conversion thing with that. Well, anyways, do the conversion and write that number down. 1.39 mil of O2 can be carried per gram of hemoglobin. That's the thing. That's the oxygen carrying capacity of hemoglobin. .39 mil O2 can be carried per gram HB. All right, so the question becomes, well, what's the oxygen carrying capacity of a person's blood? There's a couple ways you can answer that. You need to look at either the crit or the hemoglobin. So if you just want to look at the crit, it's a kind of a faster determination of a person's blood carrying capacity. It should be about half, okay? Crit is a percentage. So it's a unitless number. It's a proportion. So if you get a sample of someone's blood, you figure it out. Just spin the blood down and look at it. The blood down, I mean, all the red stuff on the bottom is the RBCs, right? And you do have the Buffy coat. Top of the Buffy coat, you got plasma. I'm going to make a top mark here. And color it yellow. Because it's like plasma is about yellowish color. Okay, so you get the idea. You can see the fractions. The crit, they usually include the Buffy coat. So you see what proportion that is compared to the top mark. Now, whatever the top mark is, it doesn't matter. The proportions matter. Okay? Doesn't matter what you measure it as. It's like you're 100%, right? Doesn't matter. Proportions matter. So you can figure it out by percentage. On the slide I have X and Y. So I call that X on the slide. The whole thing is my Y. Crit determination is X over Y times 100. So it's a percentage. And normally, let me give you a normal range. I say average is 45. The normal range is something like, NL is normal. Let me give you the low end first. 37 to 54. That's a normal crit range. That means you fall somewhere within there, 37 to 54%. Your blood carrying capacity is pretty normal. Okay. So that kind of gets into polycythemia versus anemia. If you have too much or too little blood. Before I get into that, the other thing you could do to estimate blood's oxygen carrying capacity is to take a little sample of the RBCs and see how much, well, measure the hemoglobin, measure the hemoglobin concentration. Okay. Yeah.
What happens if you have higher than the normal range of it? Like it's more than 54.
Like if you live at high altitude, it's pretty normal. Like where the air is thin, like Denver. We live at sea level. So I'll kind of get into it. What happens is, because you're getting less oxygen per breath, the body makes more blood to compensate. And that's normal and it's okay. Now you don't want the blood to get too goopy with too much blood. Then it can cause spontaneous strokes because the blood will clot. Yeah.
My baby was born 4 months ago. She had a crit of 60 and her hemoglobin was 20 for like a couple of weeks until it got normal.
Okay.
I mean, what does that mean? Like they kept trying to explain to me, the doctors, I just couldn't figure it out.
What did they say?
Why? They say it just normalizes, but they didn't explain why it happens. She was tiny, but I don't understand why.
Her crit was 60?
Yeah, and her hemoglobin was 20 for like 2 weeks at least.
Yeah, I wouldn't be too concerned with it.
I mean, it's fine now. I'm just wondering why.
What did they want it to be? For babies, it's
Well,
different.
it has to be less than 60 and hemoglobin has to be no more than like 14, 15.
Yeah, because it's more, she has more blood, so the numbers are higher. It wouldn't concern me, as long as the blood volume increases. It's probably higher because she's so small, she doesn't have a lot of volume. And so as long as she gains weight, it'll normalize. That's probably all they're trying to tell you.
Okay.
I wouldn't take any more than that, because she was small, right? It was both weight.
She was tiny, yeah.
Okay, so yeah, we're thinking once she puts on weight, the blood values are normalized. Because when you have less volume, it's like you have more crit by default. Okay. Yeah, so what you can do is you can take a little bit of blood cells, macerate them, and just measure the hemoglobin concentration. So let me give you a normal range for hemoglobin concentration. For a female, normal concentration is something like 12 to 16 grams HB per deciliter of blood. It's a normal value. For males, a little higher, maybe 14 to 18 grams HB per deciliter of blood. So you can kind of do some predictions based on the normal range. If it's a healthy male, maybe the value is closer to 18 or 16 to 18. If it's a healthy female, maybe it's around 14. If it's a female with some form of anemia, which is low blood, maybe you expect it to be less than 12. Okay, maybe it's less than 9 or something. Polycythemia means maybe you live at high altitude, so your blood level's a little higher, so maybe it's over 18, okay, like 20. Now, I put female Olympic athlete, someone who vigorously trains. The training effect is to increase your crit, okay, so you can do your event better. And so you'd expect that value to be maybe above the normal range.
How about for pregnant women?
Your blood volume should about double, but I don't know if the crit value will double, okay, but your blood volume can increase maybe to about 10 instead of 5. All right, so normals, polycythemia versus anemia. Anemia means blood. So, for example, anemia means low blood. Versus poly, which people know that means a lot, right? Well, I mean, just look at the two pictures. Ignore the white blood cells on the right. You can kind of tell, right? There's less blood here. There's less density. Not only is there less red blood cells, the shape is abnormal. This is a form of anemia called sickle cell anemia. There's the other kinds. Polycythemia, goopy blood right here. They're packed tight. Okay, so let's kind of talk about anemia first and some causes. The most common cause is blood loss, hemorrhage. Maybe you're wounded or there's a chronic problem, hemorrhoids or a slow bleeding ulcer in the gut somewhere. Blood loss is a cause. Are you iron deficient? Is it nutritional? Eat collard greens. The dark green vegetables have. There are other foods that have high iron in it. Okay, like a lot of whole grain products do. There's something called a pernicious anemia, which is a lack of B12. And B12 is important for the absorption of iron. So you need B12. So a lack of B12 could be a form of nutritional anemia. Down arrow, B12. Turns out there's a factor called intrinsic factor in the gut that helps absorb B12. So if you lack B12, it could be because you lack intrinsic factor. For example, in the elderly, the gut mucosa kind of atrophies. So that could be a factor. Lack of intrinsic factor. So there's a few nutritional things and a slide of iron deficient versus normal blood. The exposure is a little different, but I still think you can see the difference there. Notice in the iron deficient anemia how, because when there's less blood and these red blood cells, they don't have that sickle shape, but they do kind of clump together like that. And also, the closer up picture, this is from a medical textbook, here's normal. I mean, do you see some differences in the cells shown here? You see how it's like more translucent in the middle? It's because lower HB content. So they're less translucent, more illumination there. The hemoglobin content is reduced. And not only is it reduced, if you were to measure them, they're smaller. And those cells are called microcytes. So I'll turn the lights on, but I'll point to a few. There's some genetic forms of anemia. There's sickle cell and thalassemia major or minor. Genetic causes. Sickle cell anemia. There's a mutation, a genetic mutation that causes the cell to pucker or sickle, reducing its oxygen carrying capacity. The genetic mutation causes RBCs to pucker, sickle, hence the name sickle cell anemia. That first slide I showed you was a more severe case. This slide is also the sickle cell anemia. I'll point to a few of those puckered cells, like these here, or that one, or that one there. You can spot them, okay? Now, the gene was selected because, let me show you the mutation. So I think it's on the next slide here. The mutation is here, and it causes the whole cell to pucker. It was selected because the sickle trait, it conferred protection against the malaria virus in certain parts of Africa, and so it was favorable. Okay. So again, maybe you'd rather have this than malaria. Okay. So it was selected, and you still see it, and you can treat sickle cell anemia. There's blood transfusions, different things you can do to help these patients. The other kind, to go back to the previous slide, was thalassemia. There's major and minor, because you got two genes of each, right? One from mom, one from dad. The minor is you've inherited one bad gene, and you can live with that. Actually, I have that one. So my crit is like in the low 30s, and my RBCs are small, right? Like the microcytes. Remember the normal range of what they're supposed to be? 7.2 to 8.4. So mine are probably smaller than that. Okay. And but, you know, what that means is either the beta or the alpha globin is gone in one gene, can't make it. Okay, so I only got one good gene for the alpha or the beta, and so that's why my blood is lower. And I remember when I was a student, a grad student, they said, "Oh, do you want to know which one it is?" I go, "Sure." Okay, you have to pay $50 for a PCR. And no, forget it. I don't care. Yeah, I lived my whole life. I did soccer and track, so you know, I'm fine. But the point is, you can live with a minor. But what you should need to know is it's one faulty gene of either the alpha or the beta chain. Faulty alpha beta chain. I'd rather have the $50 than no. To each his own. But anyways, there's the sickle or puckled cells I'm pointing to. There's the mutation. Let's get to the other spectrum, which is polycythemia. When you're in grad school, $50 is like a lot of money. Starving students will relate to that. All right, get back to this stuff. Polycythemia, there's a kind of safe elevation of the RBCs that's okay. If you get too severe, again, you worry about the blood flow getting too gloopy, and when blood kind of gets stopped a little bit, you allow the clotting factors to accumulate. You can have a clot where you don't want it. So that's the thing you're worried about if it gets too high. And some of the effects, some of the causes are blood doping and altitude. So living at altitude usually will kind of get you a higher than normal one, but it's okay. But blood doping is a thing where an athlete will basically try to cheat and store their own blood while they train, and then right at their event, say it's a cycling race like the Tour de France, they just drop a bag of blood on themselves to increase their crit, to give more oxygen carrying capacity, to improve performance during their event. Okay. So I'll have a slide on that later, but first, if you just live at altitude, there's something called acclimatization. Your body adapts and to basically make you operate better in the thin air. Altitude is like driving up to Lake Tahoe, you know, barometric pressure decreases with increasing altitude because we live at sea level, you live under the atmosphere. We call it one atmosphere. A big column of air is on top of you, pushing down on your body. Here's you in Sacramento living at sea level. And basically on top of you is the atmosphere of our planet pushing down on your body surface. That's like one atmosphere. And as you drive up to Lake Tahoe, I mean, you get higher and higher and higher and higher and higher, so that there's like less air on top of you, so there's less pressure, so there's less, the air's thinner. And it creates a hypoxic environment. With each 1,000 feet of elevation, your max oxygen consumption decreases about 3%. I remember one time I drove up to, I forget, some mountain thing, and I got out of the car and I went on a jog. I can't remember why. I remember I was sucking air. I was like, why am I so out of breath? It's because of this. But given a few days, you acclimatize. So know these changes here. So the change is you have decreased plasma volume. Now that's not a bad thing. Basically what you're doing is you're increasing your crit, right? So you're increasing that proportion. So by default, that plasma proportion decreases. So you have improved oxygen carrying capacity, right? Maybe as high as 35 grams of hemoglobin as opposed to the normal 12 to 18. Increased pulmonary BP and vascularity, so you're basically improving blood flow to the lungs. Improved skeletal muscle vascularity, improved oxygen transport. So some of the studies that they did to get this data is, I remember one study I read, they were trying to figure out, can you train at altitude if you're an athlete, and then go back to sea level, you know, kick some butt, right? That's basically what they're asking is, and what they did was they took a group of cross-country athletes, they trained them, and then they went back down to sea level and competed, and they saw no difference in performance. They did see some improvements, but that could have been due to the fact that they were training anyways, and it probably didn't matter if you were training at sea level or altitude. Probably the only way to have these beneficial effects persist is to live there. Okay, so you can't just go there for a few days, come back, and preserve the effect. It doesn't seem to work that way. All right, so let's talk about the normal oxygenation of blood with EPO. So normally, if you go to altitude or any condition where you subject the body to hypoxia, that's the stimulus here. The response is that the kidney will release EPO. Erythropoietin, I call it EPO for short. And well, they showed a picture of, you know, the proximal femur because that's where the red marrow is. And basically, with EPO, you're going to increase crit, you're going to correct hypoxia. What they've noticed is, if you subject a person to hypoxia, but there's no EPO, crit doesn't change, not corrected. So, you know, highlights the value of erythropoietin. You need it. Yeah.
Do people with kidney failure produce EPO?
No, I imagine it would decrease. And you can get prescribed synthetic EPO. And that's another way of athletes blood dope. They give themselves the synthetic EPO, which is easily detected. Well, anyway, that's my next slide, blood doping. That's the other way you can increase the crit artificially. The procedure is take a few pints of your own blood 2 to 3 months before competition, because that's when you train. And by training, you get your blood value back up to its normal value. And just all that during that time when you're training, blood is frozen, and the day before the event, the stored blood is thawed, and the red blood cells separate out, and you just basically reinfuse, okay, your own blood, so it's safe. And so you can read different things, just to give you a little blurb. It works. Athletes wouldn't risk doing it if it didn't work. It increased performance. So the timeline of a blood doping athlete is to remove weeks prior, right? So if that's your baseline, and then you take it down several points, and then you train, get it back up to your normal baseline, and you know, day of, day before, reinfuse, you give yourself a boost for your event. That's how it's supposed to work. So don't do it. You're not supposed to. It's cheating. This report came out several years. It's kind of old news now, but I still have it in the slides as an example. Lance Armstrong won Tour de France like 7 times, and he was like the most notorious one for the blood doping. And I feel bad for the guy. He did a lot for testicular cancer awareness, but man, he was a bad guy. If you read the report, he cheated. He tried to cheat. Everyone helped him try to cheat. It was just basically bad all the way around. But the bad thing about it is you ruin your sport. Okay, I can remember watching some documentary on Greg LeMond, the great American cyclist. He actually won Tour de France 3 times. This was back in the early 80s. And I can remember he got injured in a hunting accident, but he came back. And he tried to compete again when these guys came onto the scene. He couldn't compete with them. So he was a world champ, but then when other guys were cheating, he had to drop out. So that's why you really want to regulate it in your sport. Because if people are top guys are doing it, you got to do it, right? There's other examples like remember Ben Johnson? I'm really dating myself here. Do you remember Ben Johnson? Korea Olympics, 19, Carl. Okay, no. Okay, the point of the story is you need to get it out of your sport. Yeah. It's hard. It's easy to catch if you use the synthetic EPO, because that can be detected in urine test. If you're just using your own blood, there's nothing you can detect. It's your own blood. The only thing you could do is if you like want to test, like say, do a crit measurement here, and then do a crit measurement here, and it jumps up that much. You can say, hey, wait a minute. Hey, you can't jump that many points in this amount of time. There's something going on here. And even that's not a smoking gun. It's just evidence that you probably are doing it. The best way is like during the Tour de France stages, just go into their hotel room, see if there's a bag of blood when they're sleeping at night. I don't know. It's hard to catch. It's real tough. All right, so blood typing gets you ready for Friday's lab. Let's kind of talk about that. Why do we need to type blood? You know, it's actually very important to transfuse blood for people. Like during surgeries, like millions of blood transfusions are done every year. So it's important to be able to give people other people's blood and do it safely. Way back when blood transfusions were first attempted from one person to another, immediate or delayed agglutination, that's clumping of blood, and hemolysis of red blood cells occurred, leading to death. So it's a tough way to find out you can't do it. So we have to figure out how to do it safely. It was soon discovered that bloods of different people have different antigenic properties so that antibodies in the plasma of the recipient of the donated blood will react with the antigens of the RBC surfaces of the donated blood. So let me speak simply here. Okay, if you're going to receive someone else's blood, you have an immune system. You have antibodies in your blood. They're designed to attack anything that's non-self, bacteria, a virus, anything, right? Including someone else's blood. But you want someone else's blood because you need it because you're a trauma patient or you're having surgery or whatever. So we have to figure out a way to type blood so you can figure out what blood you could safely receive and safely donate. Okay? Because your RBCs have molecules on it that can be recognized by someone else. So you give them your blood, that person's immune system could attack it. So we have to know what the different types are. And basically, here are the different types. You've got the ABO system and the RH system. These are the surface molecules that seem to account for most of the blood transfusion failures. Okay. Now, I don't expect you to know the ethnic group numbers here, but let me explain what the ABO RH systems are. These are surface antigens. So you got antigens, but you also have antibodies. Okay, these are, I think of them as surface markers. Okay, they're molecules on the surface of a RBC or any cell. Think of antigen as a word that means antibody generator. If your immune system recognizes an antigen on a non-self molecule, you'll generate antibodies against it to fight it because you're infected with something. Okay? So antigens on, in this case, RBC, but you have antibodies. They do the attacking. So the goal is, if you're receiving blood, which antibodies do you have? You don't want it to attack the blood you receive. Okay, so you type the blood. If it's the right type, you can get it. And the types are, there's the ABO system. So what that means is, if you're type A blood means the A antigen is present on your RBCs. That's what it means.
So let's say here's an RBC, and let's say that a little triangle equals A antigen. Okay, so if I put like little triangles on RBC, type A. Okay. However, you should know, in some people, they may have an antibody against A. So let me make an antibody in the same shape. Call it anti-A, for antibody against antigen A. Okay? So if you're type B, means the B antigen is present. So let's say a little circle equals B. Okay? So then I'll put a circle-shaped antibody as anti-B. So type B. Type O means you don't have A or B. They're both absent. So O is not an antigen. It means the absence of A or B. So that's the ABO system. The other antigen system that seems to be important for blood transfusions is RH. Okay. RH is sometimes called antigen B. RH antigen, sometimes called the D antigen. It was first discovered in rhesus monkeys, hence the RH. We still use the term RH. But what they do is they use plus minus and combine it with the ABO system. So if you see a positive in someone's blood type, that means the RH antigen is present. Just like if you're type A, it means the A antigen is present. If you're positive, it means RH antigen is present. Okay? So let's say, for example, I'll use a little square for RH. That equals the RH antigen. And so let's make an antibody in the same shape for any RH. There's many other antigens, but these three seem to be the ones, if you type for it, you can safely plan how to transfuse different peoples, different bloods in different people. So let's remember, when you centrifuge blood, that when you fractionate it, that the antibodies, they're the ones that are in the plasma, and that the antigens on the red blood cells are down here. Now, when you fractionate blood, when you donate blood and it gets fractionated, they save all the fractions. But most of the time, for the purposes of this test, your test, this lecture, when you donate blood, you're donating the packed RBCs. That's what you're donating. So you're donating this, the antigens. The question becomes, does the recipient have an antibody that can attack the donated blood? That's the question. So let me explain that. The donor's blood, attacked by recipient's immune system, causes agglutination. Sometimes antibodies are called agglutinins. Sometimes antigens are called agglutinogen. Oh, well, anyways, I had that on the previous slide. I would write these terms down because they're in the procedures of your lab that I have for you on Friday. Once again, antibodies are referred to as agglutinins. Antigens are sometimes referred to as agglutinogens. So it's on that slide. Agglutination may cause a bunch of things. Basically, it can cause renal failure. It could lead to death. Okay, it's a bad thing to have all that donated blood be attacked, as in this picture. Surface antigens of the donated blood, give it to the wrong person because they have antibodies that will attack it. A lot of bad things can happen. We call it a cross reaction. Okay, we want to prevent a cross reaction. The cross reaction, opposing antibodies in the recipient that encounter their target surface antigens from the donor's blood leads to agglutination. So the whole goal is to prevent agglutination. Prevent agglutination. That's the whole goal of typing and figuring it out. So, donating blood is okay if, ... You got to consider the donor's antigens and the recipient's antibodies. Now, before you can do that, we should probably go through all the blood types and hammer out the antigens and the antibodies that they would have. If you're type A negative, that means on your RBCs, let's keep track here, you only have 3 antigens to keep track of. 1, 2, and 3. So if you're A negative, how many antigens do you have? 1, 2, or 3? You got 1. And which one is it?
A.
It's the A. So what did I say? Triangles for A, right? Your negative, is RH present or absent? Negative is absent. Don't got it. You got the 1 antigen. Now, what you should assume about a person who's A negative, you should assume they have all the other antibodies, okay, against the other 2. So they would have anti-B, antibody against B, an antibody against RH. We will make that one more like a circle. Anti-B, anti-RH. And that's what you assume about a person if they're type A. So if you're A positive, you have 2 antigens present, the A and the RH. So triangles and squares to symbolize. And then you would expect that person to have the antibody against B only. If you're B negative, you would have the antibody, you would have antigen B only. Circles. But then you would have the antibody against A and RH. So B positive type. You have 2 antigens, B and RH, so circles and squares. And which antibody would this person have against A, antibody A? Okay, you could be A, it's very rare, you could be type AB, positive or negative. Type AB negative means A is present, B is present, both of those antigens. So triangles and circles. a student who was this blood type, and she would always tell me, people are so excited to get my blood, you know, the blood donor people, and it's a rare type. In terms of antibodies, only the antibody against Rh. Okay, type AB positive. If you're AB positive, let's say if you're awake, how many antigens are on the RBCs? 3. All 3 of them, the A, the B, the Rh. The A. The A, B, the Rh. And basically, well then, which of those 3 antibodies would that person have? None. None of them. If you got all of these antigens, you're going to have no antibodies against it. Otherwise, you'd be attacking your own blood. So they have no antibodies. No ABs against A, B, or Rh, exclamation point. That makes you special. There's a name for this. You are the universal recipient. Okay. Type AB. Universal. That means you can receive any person's blood. Yeah?
There is a blood type that gives everyone blood.
Yeah, I'll get to that. But first, for this one, what makes you a good recipient? What is it about this type that makes you a good recipient? You can receive any blood type and you won't cross-react. What is it?
Because you don't have any antibody.
Yeah, you don't have, I'm hearing it, this. That makes you a good recipient. No matter what blood you receive, you got this type, this is what makes you a good recipient. You don't have that antibody to attack any blood you receive, so it makes you a good recipient. Okay, is that clear? All right, let's move on. There's other types. Someone mentioned the type you can give. There's type O. O negative. Which antigens are on your RBCs? None of them. You don't have A, B, or Rh, but you probably have all 3 antibodies against those antigens. You have the antibody against Rh, A, and B. Now this blood type is called universal donor. Because of this. When you donate, what do you donate?
RBC.
The RBCs, and be sure you understand that, otherwise you confuse yourself when you try to solve the blood typing problems. If you give that to anybody, there's nothing that could be attacked, right? Doesn't matter what antibodies they have, can't attack it. So it's the universal, the O-neg is the universal donor. So if you don't know a person's blood type and they're on the table, you have to treat them. Yeah, they need blood. But that's a safe one to give. Okay. All right, so there's O positive, where you would have antigen Rh, and you probably have antibodies against A and B. Okay, so that's all the blood types. So then what do you do with this information?
Professor,
Yeah.
I don't understand why type O has antigen for Rh.
Yeah, because O only means you don't have A or B. Doesn't refer to Rh. It's a different one, different set of antigens. So going back to this, in blood typing, and you can answer the question, donating blood is okay if you consider the donor's antigens in the RBCs and the recipient's antibodies in their plasma. Then you can do it safely, once you got it all figured out. So here's a picture of what we just went through. I don't like this one because they don't include RH, they just include the ABO system, which is fine, so it's a picture you can look at. For example, type B. B antigen on the RBCs, A antibody in the plasma. Same thing we just went through. So let me kind of take you through the logic. How do you tell if it's safe to donate one person to another? So let me show you the way that you should think as you proceed through such a question. So for example, John and Peter, two people. And first consider their blood types. AB negative, A positive. Next thing, figure out who's the donor, who's the recipient. Can John donate to Peter? So John's a donor. Recipient. First consider, well, first of all, when we get to the multiple choice, let's go through John's AB negative type. If you're AB negative, the antigens you have are A and B. So triangles and circles. Which antibodies does John have? The antibody against RH. Very good. Peter is A positive. So Peter has A antigen triangles and RH antigen squares. And the antibodies Peter would have would be against B, anti-B. So circle-shaped antibody. So once you've got that all laid out, you should consider of those choices, John's antigens on his RBCs, but Peter's antibodies, right? So of those choices, which one's the correct one? B is correct. So if you want to kind of quiz yourself at home, go ahead and the next thing is, can John donate to Peter? For John's blood type, of those choices, what did we determine for his blood type? A and B on his RBCs. So choice B is correct in this list of choices. For Peter's blood type, what we need to consider are the antibodies in his plasma. And we determined he's just going to have the antibody against B. So, choice D on this list of choices. Now we can answer the question. Without even looking at that, do you see a problem? The answer should be yes, because that will attack that. We don't want that to happen. So is the answer a yes or a no to safely donate? No. Okay, but why? No. I'll give you a couple of choices here. Okay, and this is kind of where, just to show my cards, blood typing is the written part of the next lecture exam. So the reason why I say that is I want you to think about yes or no, but also why yes or no. Why is it safe? Why is it not safe? You have to tell me what cross reacts if it's not safe. No, because Peter's no, because John's B antigen will react with Peter's B antibody. Okay, so no, and what cross reacts would be a complete and thorough answer. So, yeah, let's take a break and come back. See you in about 15 minutes.